Ben Goertzel here. Welcome to part 3 of this video talk series on the general theory of general intelligence. So in part 2, I talked about the Patternist theory of mind, the philosophy that a mind can be, from many perspectives, especially AGI engineering and cognitive science perspectives, viewed as a set of patterns associated with an intelligent system. Now, in this iteration, I'm going to dig a bit deeper. I'm going to look at some of the math and some of the philosophical concepts underlying the concept of pattern, things like distinction and observation and simplicity. You need to think about to even define what a pattern is. And what's interesting is this has more than a philosophical interest. Some of the same math structures that underlie the notion of a pattern turn out actually to be very useful for creating inference engines, program learning engines, knowledge representations, and so forth that help AGI systems manipulate patterns, recognize patterns, do reasoning on patterns, and so forth. So, this is kind of a difficult section of this video talk, and a difficult section of the general theory of general intelligence paper that the series is based on, and that it's quite mathematical and intricate, yet it goes very rapidly through a whole bunch of math concepts. So for those who don't have much technical background, there's a lot that's going to be totally confusing and opaque. On the other hand, for those who do have a mathematical background, it's going to be too fast and not go into enough detail. But that's sort of the nature of the beast. It's a high level overview. It'll give you a vague idea of what I'm talking about, and it's up to you to dig deeper into the associated paper and its references and links. So let me share my screen and get going here. Foundational ontology, I've called this section. It's in some ways a very mathy form of foundational ontology, but I mean, I think I'm viewing math here as a language for talking about fundamental forms and structures that would be even more confusing if you tried to describe them in the ambiguity of natural language. So, starting with distinction, the most basic concept or fundamental element there is. I mean, any concept that you could name makes a distinction between those things that are instances of that concept and those things that aren't. So in that sense, distinction is the most fundamental element of all. And G. Spencer Brown, in his amazing little book, Laws of Form, that I first read in the 1980s and revisit time and time again. So he articulates distinction, he notates it in the way you see in the slide here, and he then looks at two different ways of combining two distinctions. If you get another distinction, you can put the distinction side by side, that yields a distinction. You can nest one distinction in another, which yields what we can call a void. And one thing Spencer Brown shows is that this is isomorphic to Boolean logic. Spencer Brown wasn't the first to realize that Boolean logic could be achieved with just one operator instead of the three operators and or use, but he did it much more elegantly than everyone else, and he explains how predicate logic can be gotten through some minor extensions to this formalism of distinctions. As one trivial example, you get implication A implies B. It's not A or B, or it's A with a distinction mark over it side by side with B. And where it gets even more funky and interesting is when you try to go beyond the void versus distinction and look at paradoxical truth values. So you can look at the unmarked state, just blank, as reflecting falsehood. There's nothing there. Then you can look at the marked state with the distinction as reflecting truth. Actually, there's a symmetry there. You could call the blank state truth and the marked state falsehood if you wanted. Everything works out just the same. But for convenience, let's call the blank state, let's call the void falsehood and the distinction the marked state truth. Then if you look at an equation like F equals not F, which we see here. I mean, one thing we see is that neither truth nor falsehood, neither the marked state or the unmarked state works, right? Because neither of them fulfills that equation. So X equals not X is not fulfilled by either true or false, right? So then an observation made by Lou Kauffman in his beautiful essay Sign in Space, which I also read in the 1980s. And you know, when I read this essay, I loved it so much, I wrote Lou handwritten letter, which is the thing you did back in the 1980s. I was in my first years of grad school. There were no email accounts for grad students yet. I had a brief correspondence with Lou. He sent me some more of his papers. I got to know him again more recently, and we've chatted back and forth. His work is still amazing. You can look up Louis Kauffman at University of Illinois, Chicago, I believe. He's got a bunch of amazing stuff on the web in physics, philosophy, and math. But one observation he made way back when in his paper Sign in Space is that if you have an equation F equals not F, there's sort of two ways to look at the solution to it, right? And then I've just scribbled these down on a piece of paper here. So you have F equals not F. You can sort of look at it as the alternation true, false, true, false, true, false, or as the alternation false, true, false, true, false, true. There's two infinite series you could look at as resultant from this paradox. And he calls one of these I, the other one J, and he's looking at these as two imaginary truth values. So as he's looking at it, the paradox F equals not F is resolved by introducing the time dimension. And F equals not F, you can have the infinite oscillation true, false, true, false, true, false, or the infinite oscillation false, true, false, true, false, true. They're both viewed as infinite in two directions. And in either case, if you negate it, you get the same thing back if you negate it term by term. So that's interesting. There's an analogy with that with complex numbers, and you can extend this in various ways. So we can look at four simple truth values coming out of this. So we can look at, say, two component truth values where you have distinction, true, void, false, and then the two imaginary truth values, false, true, and true, false. And we see these four simple values here. Then we can also define on these two component truth values an operation which is the square root of not. Like you iterate it twice and you get not, which is, it's kind of cool. In ordinary Boolean logic, there is no square root of not, right? So the square root of not operator, the imaginary distinction is shown here. You apply the square root of not to a comma b, and you get not b comma a. And of course you do that twice, you're going to get not a comma not b. You're going to be negating both components. And this is not just funky and cool, but it's the root of some interesting connections between laws of form distinction logic and both quantum logic and paraconsistent logic. I unravel some of these connections in the paper Paraconsistent Foundations, and then a companion paper, Paraconsistent Foundations for Quantum Probability. I'm just going to allude to very vaguely to some of those concepts here. But if you're familiar with the complex plane, this picture will get the analogy across, right? I mean, you have true and false along the horizontal axis, and the two imaginary truth values along the vertical axis. And the square root of not operator has, in essence, the impact of rotation by 90 degrees. It's very similar to what we have in the complex plane, and making that morphism between these imaginary truth values and imaginary numbers actually work is weird and subtle, and in a certain sense it seems to work only within the small margin of error. And I wrote about that in the paper Paraconsistent Foundations for Quantum Probability. We don't really need that for the general theory of general intelligence on classical computers anyway. I'm not going to go too deeply into it here. What I do want to go into is the mapping between laws of form and paraconsistent logic, because paraconsistent logic maps directly into probabilistic logic networks, uncertain logic, which is extensively used in my OpenCog approach to AGI. So this is getting from the philosophical rapidly toward the practical. It's wonderful when things with this profound philosophical and foundational meaning end up connecting directly to the algorithms that you're using to do real world stuff, right? So there's something called intuitionistic logic, which if you're not familiar with it, I'm not going to try to convey fully here, but it has to do with the ability to make mathematical proofs constructive, right? So in ordinary classical mathematics, if you want to prove something exists, there's two ways. You can give a sort of method for constructing the thing, and that's obviously a way to prove it exists, or you can do a proof by contradiction. You can say, well, I'll assume this thing didn't exist, and then I'll show that leads to a contradiction, and therefore the thing must exist. So in intuitionistic logic, you can't do this proof by contradiction except when it's a shortcut for a constructive proof. So the only kinds of proofs that are really accepted are proving something exists by showing how to build it. And so an example where that doesn't work is, say, an uncomputable number. So there's no algorithm, there's no procedure for building an uncomputable number. You can show it exists only by contradiction, like assume it doesn't exist and you'll get a contradiction in certain logic. So in constructive math and intuitionistic logic, you don't have those uncomputable numbers because there's no way to prove they exist by constructing them, right? So this, I think, is very powerful and ties in closely with AGI, because as I view in AGI, it's abstractions or things that should be able to build up constructively from its observations. We have a lot of crazy abstract ideas, but ultimately we should be able to construct them from concrete observations that we had. And so that's very high level, but then you get into a lot of devilish details, right? So in standard intuitionistic logic, there's an asymmetry between true and false. Like in laws of form, true and false are symmetric. Whether you say the void state or the distinct state is true or false doesn't really matter. In standard intuitionistic logic, true and false are not symmetric. Basically, a constructive proof of something is needed to show it's true, then false just basically means you can't assume it's true. And there's actually a dual logic to that, which is falsification logic, which underlies, for example, Karl Popper's philosophy of science, where in Karl Popper's view of science, you can never prove a scientific hypothesis true. You can only prove it false by giving a counterexample, which falsifies it. So right, in standard constructive math, you prove true by construction. False means, well, you can't assume it's true. In Karl Popper's philosophy of science, a scientific hypothesis can be shown false by giving a counterexample, but there's no way to show it true. True just means you can't yet assume it's false. Now, there's a symmetric way to do it, which is called constructable falsity logic or constructable duality logic. And here you need examples on both sides. To show something's true, you need to show an example that it's true. You need to show a way to construct the thing. To show something's false, you need to show a counterexample, a specific example that makes a thing false. And I think that's the way to do it. That's the way that comes naturally out of laws of form. It's symmetric. And the most really stunningly beautiful realization of this idea is Anna Patterson's constructable duality logic, which I review a bit in my paper, Paraconsistent Foundations. I mean, this is a really, really nice logic system. And, you know, the essence of it is given here, but the math goes quite deep. And you can see there's four truth values here, right? And these four truth values, it's not hard to see, they're the same thing as they're not aligned with each other here, because I was lazy and cut and pasted pictures out of the relevant papers, but you can see they're the same as the laws of form truth values, right? I mean, you have 0, 0, 1, 1, 1, 0, 0, 1. Now, I actually, Patterson uses 0, 0 for false and 1, 1 for, well, 0 in Patterson's scheme, the first component is positive evidence, the second component is negative evidence, right? So in her scheme, basically, if you want to say, I have only positive evidence for something, then you're saying the thing has a truth value 1, 0. If you want to say I have only counterexamples, only negative evidence, you're going to say that's truth value 0, 1. If you want to say, well, this is wacky and confusing, I have both positive and negative evidence, both examples and counterexamples, 1, 1. And if you want to say that you have neither positive examples nor negative examples, then you get 0, 0, right? So these are not the same labeling as in the laws of form. On the other hand, you can one-to-one map among them. There's a natural morphism between Patterson's truth values and the laws of form truth values, which is quite elegant. And then you could look at laws of form as an elegant way of building up to something that's isomorphic by a simple transformation to Patterson's logic. And Patterson then elaborates this logic in terms of lattice theory. And if you look at the operations, it's a bit subtle. So if you have, say, x prime and y prime, then that comes out to x and y comma x prime or y prime, right? So if you look at how these operations work, they have to be cashed out in terms of the logic of what's positive evidence and what's negative evidence. So you're doing logic on positive evidence set comma negative evidence set, and this lets you have a very consistent, elegant, symmetrical approach to reasoning about complex, paradoxical, contradictory, confusing situations. And one thing I've found is that you could map Patterson's paraconsistent logic pretty directly into the PLN probabilistic logic that we use in the OpenCog system. And the way to do that has to do with counting observations and counting evidence. So suppose you want to make Patterson's constructible duality logic uncertain, right? Then what you're going to do, you're not just going to say either I have an example and or a counterexample. You're going to say, how many examples do I have? How many counterexamples do I have? Like, how many pieces of evidence do I have in favor of this? How many pieces of evidence do I have opposing this, right? And that's kind of the same thing we do in PLN logic. We have a hypothesis, and we count the number of pieces of evidence in favor of it or opposed to it. And then the difference between the PLN logic and the paraconsistent logic from Anna Patterson, I mean, the difference is in how you normalize these evidence counts, right? So in PLN, what you do, you look at the number of positive observations, the number of negative observations. These are called n plus and n minus in the slide here. And you normalize them by the number of total observations. So the strength, which is like a probability, is n plus number of positive observations divided by n plus n minus number of positive plus number of negative observations. And that gives you a probability. Then the sum of n plus n minus n is the count, which is like a measure of the weight of evidence behind that probability. If the count is bigger, then that probability is in a way more certain. There should be a smaller confidence interval around it. What you have to do to get paraconsistent logic instead is look at an ensemble of situations. And in each situation, you could see positive evidence in favor of your hypothesis. You could see negative evidence in favor of your hypothesis, or you could see both, right, in each situation. And then what you do, you count the number of positive evidential observations about your hypothesis divided by the number of situations. Or you count the number of negative evidential observations about your hypothesis divided by the number of situations. And then that pair of numbers, n plus over n, comma, n minus over n, that pair of numbers gives you an uncertain paraconsistent truth value. And so it's a different normalization. Do you normalize by the number of evidential observations or by the number of situations? In one case, you get a traditional probabilistic truth value with a weight of evidence as well. In the other case, you get a paraconsistent truth value, where in the extreme cases, you could have, say, 1-1 if every situation had both a positive and negative piece of evidence in it, 0-0 if there's no evidence, 1-0 if every situation had positive evidence, none had negative evidence, 0-1 if every situation had negative evidence, none had positive evidence. So there's a simple isomorphic mapping between these paraconsistent truth values that I call p-bits in the paper, Paraconsistent Foundations, and PLN, probabilistic logic network simple truth values. And that's interesting because paraconsistent and probabilistic logic they're not normally thought to be the same thing, right? And you can take this mapping further. You can map the paraconsistent truth values into quantum probabilities. I mean, I don't want to go into that too deeply here. There's a certain approximation error in the mapping. It's kind of messy, but I think it's very interesting that these different logic systems with very different interpretations and different rules, I mean, they can be mapped into each other, and then each of these sort of isomorphic views of what's in a way the same logic system, each of these different isomorphic views, be it laws of form, paraconsistent logic, probabilistic logic, quantum probability, each of these isomorphic views is more convenient in different contexts and situations. And this sort of it's an illustration of something much more general in how minds work, right? So very often when you're looking at how an AGI system or a human mind, how a generally intelligent system does things, what you find is there's many equivalent or roughly equivalent ways to represent the same thing. You have morphisms mapping between the different representations, and then the choice of which representation to use in a given context is important because of computational efficiency, because some representations make it much more efficient to do certain kinds of manipulations with low error, right? And then this leads you into issues like cognitive synergy that I'll talk about a little later, where if you're using one representation to do some learning or reasoning or perception or action generation, whatever, and you run into problems, maybe you want to map into another fully or roughly isomorphic representation where a different algorithm can operate more efficiently, then get an interim conclusion and map back, right? So we're seeing inklings of this general property of cognitive systems here in these various morphic versions of logic systems that we're exploring when looking at how distinctions are combined as part of the underlayer that I'm using to build up to formalizing the concept of pattern. And yeah, the next thread I want to introduce here along these lines is a notion of a distinction graph. And this one is my own peculiar concoction, which I came up with when doing some thinking about the foundations of entropy, actually. So entropy is normally formalized in terms of partitions, which are in essence partitions of observations made by some observer. And partitions are important. Partitions are great. On the other hand, partitions aren't the bottom layer. They're not the most fundamental thing, because if you think about it, the observations made by a real cognitive system observing things are not partitioned into discrete categories, right? Take an example like light red, middle red, dark red. So light red and middle red, I may not be able to tell apart. Middle red and dark red, I may not be able to tell apart, but I can still tell light red and dark red apart, right? So then my observations are not necessarily partitioned into discrete subclusters where the elements of one subcluster are indistinguishable from each other and the elements in different subclusters are distinguishable from each other. That's not really how it works, right? So instead you have what I call a distinction graph. Each observation relative to some observer is a node. You can draw a link between the two nodes if those observations are not distinguishable from each other by that observer. And so like in the case of this picture on this slide, if A was light red, B was middle red, C was dark red, you might have A and C distinguishable, but A and B or B and C are indistinguishable, right? And this sort of distinction graph is a more fundamental representation of the relation between observations made by some observer than a partition. And you can look at entropies built on this distinction graph, which I do in a paper called Distinction Graphs that you can find on arXiv. So Ellerman introduced something called logical entropy. The logical entropy of a partition basically is the proportion of pairs of elements that are separated within the whole partition. So graphtropy generalizes that from partitions to distinction graphs. The graphtropy of a distinction graph is a percentage of pairs of nodes that are not linked in the distinction graph. And this reduces to logical entropy in the case of a distinction graph. That's a collection of disjoint, completely connected subgraphs. So you can then layer partitions on top of the distinction graph, right? You can say, well, let's make a concept node which groups only certain nodes in the distinction graph. And you can make a member link, like between the node symbolizing the concept node or the partition element and the nodes that are its members. Then you can make fuzzy distinction links between these concept nodes and say, well, if they're totally disjoint, then that's one thing, but they may somewhat overlap. Then you can have a weight, and you can have partially distinguishable concepts, but this is built on the underlayer of the underlying distinction graph. Then you can build more complex graph structures on top of these. And this is important in terms of AGI, because I think graph structures and their derivatives are important both for describing AGI systems and analyzing them, and they can be a valuable core representation to use in building AGI systems. So, you're familiar with the notion of a graph. You have nodes and links. It could be weighted and labeled, directed, undirected. There's a notion of a hypergraph, which is like a graph where you can have a link spanning 3, 4, 5 or more different nodes. In a metagraph, you can have links pointing to links. You have links pointing to whole subgraphs, and you can build these from distinctions. Like a distinction metagraph, you have a link that's a distinction between two links, a distinction between two distinctions. You can have a link that tells how distinct two different distinction graphs are, and building this up gets you closer and closer to an adequate representation for describing or building AGI systems. So if you have temporal relationships between your observations, say before and after relationships, or even timestamps or something, then you can get from that, you can derive links representing simultaneity or links representing temporal implication, like when these things both occur at the same time, that A and B, then C will occur after that, right? And once you have these temporal relationships, well, then you can build decision trees and decision DAGs, directed acyclic graphs. And this example has numbers in it, like when the input x1 is greater than 5. If that's true, then you ask, is x2 less than 7? If false, you ask, is x3 equals 0? But it's well known how to build judgments like greater than, how to build numbers out of basic sets and groupings, right? So once we have distinction graphs and we have partitions like concept nodes, sets of nodes within the distinction graphs, and we have time, then we can do numbers and we can do decisions, and you can go further. You can make decision graphs that take other decision graphs as inputs, right? Which is what I call combinatorial decision graphs, combinatorial decision DAGs. And I have a paper on arXiv about those. And this gives you a Turing-complete computational model, which is closely related to combinatory logic. So once you get there, once you get to these decision graphs built up out of distinctions and temporal distinctions and groupings of distinctions, right? Then you've gotten to the point where you can basically represent arbitrarily complex computable functions, taking inputs and mapping them into outputs. And you've built up an infrastructure out of distinctions, time, and ensuing graphs that lets you talk about patterns. So we're back to Patternist philosophy, finally having built it from the ground up, step by step. Although in this presentation, obviously, I skipped a lot of steps and just pointed at them. So this is the good old definition of a pattern that I gave in my book, The Structure of Intelligence, in 1991. It's still, I think, a good way of thinking about it, that you can add some more color. I mean, a pair fx is a pattern if combining f with x gives you y. And for example, if f is a function, combine can mean plugging the input x into the function f. And you know, the complexity of f plus simplicity of y is less than the complexity of f plus the complexity of x is less than the complexity of y. So for example, if the complexity of f is just the length of f in a certain language, the complexity of x is the length of x in that language, complexity of y is the length of y, I mean, then this basically means that the length of f plus the length of x is less than the length of y. So you've represented y in terms of stuff that in composite is shorter than y, right? So that this becomes an information compression sort of measure. But the measure sigma here doesn't have to be length. It could be runtime, it could be amount of energy used, it could be a lot of different things. So basically, setting aside the math, a pattern is a representation as something simpler. And in order to say that, you need to be able to talk about representation, meaning you need to be able to talk about programs or functions that can combine with other things to produce other things, right? And so we built up to that from elementary distinctions in a certain way. Then we got to the level where you could talk about patterns. And I've been through this more recently in a paper on Occam's razor and simplicity, which is also on arXiv.org. Tried to look at this build up to the concept of pattern in a more systematic way. I mean, if you have a bunch of entities endowed with a set of binary operations that combine the different entities in different ways, you can almost think of this as like a chemical model of computation. And in this paper, I do refer to some other papers that explicitly describe a chemical model of computation, like things are computed by elements combining to form new elements, which combine to form new elements, which combine to form new elements. I called this a magician system back in the early 90s, so that name never caught on. Now I call it a combinatory model of computation. Basically, if you look at computation this way, which is a perfectly valid general purpose way to do it, then you say, well, we can model the simplicity of some entity in terms of sort of what's the minimum cost to build up that entity through repeatedly combining elements with combinatory operations, and combine the combinations, and so forth. So a measure of simplicity that can be defined as the minimum cost of iteratively combining a bunch of elements with combinatory operations, I call a combinational simplicity measure. Program length, program runtime are examples of these, and you can use this notion of a combinational simplicity measure to give a slightly more sophisticated version of the definition of pattern, which is run through in the paper on general theory of general intelligence, and then in more detail in my paper on Occam's razor. And you can use this, kind of the chase a bit, you can use this to give a very interesting perspective on the appearance of hierarchy in intelligent systems. So we can define what we call a sub-pattern hierarchy, where Y is a child of X in the sub-pattern hierarchy if Y is part of a pattern in X. So Y is a child of X if you can combine Y with something else to make X in a way that constitutes a representation of X as something simpler. So here in this picture, you see Y as a child of X in a sub-pattern hierarchy, because Y combined with Z yields X in a way that adds additional, in a way that confers additional simplicity, right? So this kind of sub-pattern hierarchy, I think, is very important in cognitive systems. I mean, the idea that hierarchy is important in minds is now very much in vogue because of visual hierarchies and hierarchy of layers and neural networks and so forth. But I think the notion of a subpattern hierarchy explains more fundamentally how hierarchy appears in cognitive systems. And there's some interesting theory here. So if you're looking at patterns in systems that are defined by a combinatory computational model of a bunch of elements combining with each other to form new things. If you look at patterns in this sense, you can see that if the operator set, the set of combinational operations, is approximately associative in a certain sense, then your subpattern hierarchy is nicely transitive. And so that's kind of important, right? So I mean, say you have a subpattern hierarchy where Y is a subpattern in X, it's part of a pattern in X, and A is a subpattern in Y, it's part of a pattern in Y. Then do you know that A is a subpattern in X? Is subpatterness transitive, right? If you don't have that, you don't really have a very good hierarchy, right? So I mean, like you could look at like the nose is part of the head, the nostril is part of the nose. So the nostril should be part of the head too, right? I mean, you want to have that transitivity in a subpattern hierarchy. And what this theorem in my paper on Occam's razor shows is that you can get this associativity, you can get this rather transitivity in this subpattern hierarchy if the underlying combinational operators in your combinational computational model are associative. And that's pretty interesting. I mean, you got to look at the paper to see why it's actually kind of obvious, but this is another thing that has multiple resonances and implications across AGI theory, because when we get to representing various cognitive algorithms in terms of a combinational computation model, we'll see that associativity of combinational operators is important also in terms of getting efficient ways of executing cognitive algorithms. Like if you have a cognitive algorithm that's implemented in terms of combination of a bunch of simpler elements, if the combinational operators are associative, then you can implement that cognitive algorithm by way of Galois connections as different kinds of folding and unfolding operators, which is a very efficient way to do it, which leads us directly into various aspects of OpenCog Hyperon design. So we see here associativity or approximate associativity among the combinational operators in a combinational computational model. It's important for a bunch of reasons. Like it gives you representational hierarchy in the sense of subpattern relations that are approximate partial orders that are really appropriate subpattern hierarchies. And it also gives you cognitive algorithms you can implement by folding and unfolding. So associativity it's a really, really nice property. And it also helps you get what I call dual networks, or a dual network is a hierarchy that's also a heterarchy, right? So in a dual network, things that are grouped together in a hierarchy, like say Q and P or H and S here, will also tend to have a lot of properties in common. So if you have a hierarchy where the things that have the same parents in the hierarchy also have a lot of properties in common, they're also similar, you have what I call a dual network. And I wrote about that a lot in my book, The Evolving Mind in 91, and Chaotic Logic, which was published a couple of years after that. You can get dual networks very naturally once you have subpattern hierarchies that are proper hierarchies with the transitivity property. And this has to do in subtle ways with Occam's razor, right? So Occam's razor traditionally is just prefer the simplest hypothesis. And if you have multiple measures of simplicity, like you care about program length and runtime and energy usage or something, right? I mean, then you can say prefer hypotheses where their simplicity measurements according to your multiple simplicity measures are a Pareto optimum. What you find is that these simpler hypotheses are also, these are hypotheses that let you construct coherent dual networks across your observations. So there's a lot of subtlety between this simplicity of the patterns and programs that you're finding and the way that networks of observations are structured. And this ties in with so many different things. And another interesting thread in this tapestry is the way probability theories depend on these graph structures. So you're building graphs out of distinctions, and you're building graphs then out of patterns, like these sub-pattern hierarchies and corresponding heterarchies. And once you've built up all these graphs from the basics of distinction and information and whatnot, you can then define probabilities on top of these graphs, right? So normal probability theory, like you probably learned about in school, comes from sets and set union and intersection, right? You have a sample space and you look at subsets of the sample space, and you can then define probabilities that work well with the Boolean algebra on the subsets of the sample space. But if you have a graph instead, like the graph built up by a mind in understanding the world and making distinctions and groupings and recognizing patterns, if you have a graph instead, then what you want to do, you want to define probabilities on these subgraphs. And it turns out there you want to use what's called a Hating algebra of subgraphs rather than a Boolean algebra of subsets. And you get an intuitionistic probability theory, which then ties in beautifully with intuitionistic logic that I already mentioned is coming naturally out of laws of form and leading to paraconsistent, constructable, duality logic, and so forth. So the intuitionistic logic that comes out of looking at basic distinctions when you tabulate probability, positive and negative evidence in the right way, the same intuitionistic logic pops up again when you're looking at how do we try to build a probability out of the subgraphs of this distinction graph, right? And it's yet another beautiful parallel. And the reason this is an intuitionistic logic has to do with the nature of negation here. I mean, in this sort of Hating algebra on subgraphs or submetagraphs, if you have a graph X, the negative of that graph X is a collection of nodes that aren't in X and the links and interlink them, but neither X nor not X subgraph contain the links between the nodes in X and the links in not X. And this means you don't have the law of excluded middle that you have in classical logic, and it gives you a slightly different probability theory, which is an intuitionistic probability theory. And it's quite beautiful that the best way to reason about the subgraphs of this distinction graph or knowledge graph that we've built up is intuitionistic logic, which is immanent in the distinctions that you use to build up the distinction graph in the first place, right? And yeah, the final thread I want to weave in here, just to make things a little weirder if they weren't weird enough yet. The final thread I want to bring in here is a different interpretation of graphs, which ties back to Spencer Brown's preoccupation with paradox. I mean, so in classical set theories, or Malafranco set theory, you have something called the Axiom of Foundation, which says no set can contain itself as an element, right? So, but what if you want a set to contain itself as an element? Well, you use, for example, Axel's anti-foundation axiom. Then you can make a set that contains itself as an element and as a circular membership graph, like the one I'm drawing here. And I use this in a paper I wrote some years back to model things like self and consciousness. So you could say, my consciousness of this tree, my reflective consciousness of this tree, is the correlation of my reflective consciousness of the tree with the pattern representing that tree in my mind. So it never bottoms out, right? And this sort of graph defining a hyperset, it's in a way it's just a different interpretation of a distinction graph. And then the mapping between the basic distinction graph and the graph that connotes a hyperset with circular membership, this can be viewed as sort of the mapping between an observation oriented and a reflection oriented view of the same graph. So again, a morphism between two different perspectives that are equivalent in a way, but different in a way also. It's dinner time. I'll come eat dinner very soon, okay? Okay, bye-bye. It's dinner time, but fortunately I'm almost done with recording this one. So reflective self, you can model similar way. Ben's phenomenal self contains his representation of his parrot. Well, I missed that parrot. She's been gone a while. Ben's self contains a representation of this parrot to the extent that Ben's representation of the parrot being part of his self is correlated with the representation of the parrot. These things are hard to say in words, easier to show in diagrams, easier still to write in equations. And this sort of reflexive hyperset interpretation morphically maps into a laws of form representation in this graph, which maps into paraconsistent logic or a quantum probabilistic or a PLN representation. Choose your task and choose your representation, right? And taking it a little further, you can look at, say, Axel's solution lemma shows if you have a finite set of interreferential equations like X is I know you know Y, Y is I think you believe X, right? And then he shows there's some hyperset fulfilling that. Well, in Patterson's constructable duality logic, you show if you have a system of paraconsistent logical equations, even if it lacks a least fixed point, it may have a unique possible fixed point. And she uses something called implicit programming to find solutions there. This maps interestingly into Axel's solution lemma, right? Again, different formalisms, but there are fairly clear mappings between them. I haven't written this one out in any paper yet, actually, but it's there, right? So yeah, this has been really like a Mr. Toad's wild ride through a large number of different formalisms, which give different perspective on distinction, pattern, probability, paradox, and related concepts. I mean, you could do a whole in-depth lecture series on these different formalisms and how they interrelate. And in the papers I've written on this, I've just kind of sketched out and indicated things because I've been too busy, running companies and building systems, and haven't had time to write out so many proofs. But I hope in this talk I have been able to at least convey to you the sort of formalisms and ideas that I think are important for constructing knowledge representations and cognitive algorithms. So in the next iteration in this series, I'm going to get, I hope, a little less confusing and sort of herky-jerky and all over the place. I'm going to talk about how do we define what is general intelligence, and then get into algorithms for realizing general intelligence, both some very elegant algorithms that can't be implemented due to efficiency reasons, and then some more realistic types of algorithms that are in a way specializations of these elegant and infeasible algorithms. And when we get to these realistic cognitive algorithms that are specializations of elegant but infeasible cognitive algorithms to realize general intelligence, then we'll see a bunch of these formal structures that I've been sort of dancing chaotically through in this lecture. We'll see these formal structures pop up in some quite interesting ways.